Hey folks, Todd Coburn here with your Aerospace Structures series. This is lecture 2 for our Composites course. And in this lecture we're going to be covering some of the nomenclature, concepts, materials, and methods. So kind of an overview, but now we're starting to build key information that we're going to be using over and over again in the course. So we kind of ended our last class by looking at the kind of materials we might encounter, and we talked about which ones we need these methods for and which ones we don't. And so now we're ready to start talking about some basic terms. We talked about this a little bit before about a composite being thought of as a material constructed of two or more materials, but made in such a way that it can't be loosely idealized as being isotropic. And when we talk about this, what we're talking about is these pieces of material that we're putting together. We're putting together so they behave as one, and we can call that like a macroscopic view of how they behave. We can look at the microscopic behavior, how they behave on their own. But what we're really looking for is not the microscopic behavior, but what is the macroscopic behavior. Now we're going to find that sometimes we're going to need to dive back down into the microscopic kind of behavior, and some folks say that's the way you have to do all this analysis, although I disagree with that. There is times when that would be necessary or appropriate, but there's many times where we can, having characterized the pieces and characterizing the macroscopic behavior of the composite, we often can get away with analyzing right at that level. That's what we're going to be doing. So a macroscopic combination is something, we could think of that as something that we can see with the naked eye. Actually, probably a better way is we can characterize it with testing. So if we have, let's say, a continuous fiber, let's say we have a layer of material made of an isotropic material, we could talk about the macroscopic capability. If we have a layer of material constructed of, say, continuous unidirectional fibers, we can go and test that layer and see how it behaves as a whole. Even though there are various pieces within that layer, we're going to be looking at the macroscopic or the overall behavior of that layer. And when we get to like composite laminates, we're going to be doing that macroscopic look at each level, and that's how we're going to build up our analysis approach. So the macroscopic level, we can loosely call it something that we can spot with the naked eye. Okay? This is in contrast to something that is microscopic, for example, and when we say microscopic, we could be talking about super tiny. We're not really talking about that. What we're basically saying is, like for this continuous fiber element, element D up here, we have fibers and we have matrix. Certainly there is a much lower level of microscopic level of how we could view these pieces. What we mean by this term is we've got the fibers. We can look at what the fibers do on their own level. We're going to call that the microscopic level. How the matrix behaves on its own level, we can call that its microscopic behavior. And then we're going to look at the macroscopic performance of the two acting together. That's how we're using those terms. All right, the next thing is the idea of homogeneous. So homogeneous basically means it's the same everywhere. A homogeneous material has uniform properties throughout, and inhomogeneous has material properties that vary from point to point within the body. Now, when we're constructing a material of multiple pieces, say fiber and matrix, certainly that's not homogeneous, but we can kind of say, well, loosely this is going to behave at the macroscopic level as if everything in this direction is the same, everything in this direction is the same. Okay, so in that sense, we're going to be using that homogeneous word. We also have the idea of trophy, isotropic and anisotropic and orthotropic. An isotropic material is one that is the same, properties the same in any direction. So you take any point and it's the same in all directions. An anisotropic material is one that's different in all the directions, and an orthotropic has three mutually perpendicular planes that we can deal with. For example, if we have a unidirectional fiber, it's typically going to have a longitudinal property, that's one direction. Perpendicular to that is its widthwise property, and transverse to that is its thickness-wise property. If we have a woven material, same story, we can have a longitudinal or a warp property, perpendicular to that a widthwise property, a weft property, and perpendicular to the two of those is the through thickness property. So we're going to be dealing with materials that have different, are more complicated and are not just isotropic. We looked at the whole directional material thing, these chopped fibers, and the oriented fibers could be distributed so they give a unidirectional, so this random fiber could potentially act like a homogeneous material. The continuous unidirectional one is going to behave in a very probably orthotropic fashion. We're going to have one property lengthwise and one property widthwise, and potentially another property through the thickness. Same thing's true for the oriented samples. But for a woven sample, we're going to end up getting different properties in the two perpendicular in-plane directions and another property in the out-of-plane direction. Although it is possible that these two in-plane directions will have the same property. Now the trick here is, if it has the same properties in the longitudinal direction as it does in the widthwise direction, it starts looking like it's isotropic. But it's not, because if you rotate your little element, look at it in another level, it's going to have a totally different, if you look at it in this level, it has a totally different stiffness. And that's what we're going to be dealing with. So what happens when we have materials that are, this little graphic that is kind of explains that. If we had an isotropic material, if we pull on it in a unidirectional fashion, it gets longer, strains, but it also gets narrower in the other two directions. That's very predictable. In the same way, if we have that isotropic material, a flat plate-like element, we load it in shear, pure shear, it's going to rotate, it's going to behave like this, where it kind of slides over, and it's going to be, it's going to follow a very predictable behavior. So if we have shear loads applied, we're going to get shear deflections, shear strains. If we have normal loads applied, we're going to get normal strains and deflections. Now, on the other hand, if we have an anisotropic material, then if we pull on it in the longitudinal direction, not only will it have extension and contraction, but it also will shear the material. And if we apply a shear instead, it not only will experience shear deformation and strain, it will also experience extensional deformation and strain. That's a lot harder to predict. Now, if we have an orthotropic material, that's one where we have three mutually perpendicular directions of material properties, then if we load it in its principal directions, it will look kind of like it's behaving like an isotropic material, where axial load gives axial and transverse deflections. Shear load gives shear deflections. But if we load it in a non-principal direction, then we can see anisotropic kind of behavior, where the thing can get shear deformation from an axial load and axial deformation from a shear load. So that's a little tricky. We're going to be dealing with those kinds of things. All right, so we're going to be using this term lamina to talk about a layer. Remember, we talked about different materials. We're going to be focusing on those and how those properties are. We're then going to look at what the properties of a laminate are when we have multiple layers of different materials. And we're going to call that whole stack a laminate, but we're going to call each layer a lamina. Now, to get technical, we like to use that lamina term, but really we call it a layer or a ply. It's nearly interchangeable. So if we say apply material ply number 3, we're talking about the third layer. If we talk about ply number 5, we're talking about the 5th layer. If we talk about layer 3, we're talking about the 3rd layer. And all of these terms, if we're talking about the 6th layer, we really mean lamina number 6. And when we number these, we'll get to this later, we're going to be numbering them top to bottom, 1 to whatever layers or lamina. So each lamina we're going to focus on what are those properties. We need to understand what those properties are on a macroscopic level. We might need to figure out the microscopic properties and use those to estimate the macroscopic properties. Once we have the properties of each and every layer, then we can start applying our classical lamination theory to evaluate the laminate itself. Okay? So we can actually put any old material in each layer. Here's a few examples of those. Here's a little picture out of Jones' book where we see a unidirectional lamina versus a woven lamina. And we've got the 3 mutually perpendicular material directions, the warp, the fill, and the transverse. We call them warp and weft, and that weft word could be fill. Because the reason we do that is when they're weaving these fabrics, they will often have them come off a machine that rolls that fabric out. And while they're rolling out that fabric, they'll have another those fibers in the longitudinal direction, the warp direction. They'll have another thing that's weaving in the fibers in the other direction, the widthwise direction, in the widthwise direction, which we call the fill or the weft direction. So those terms are what we're going to be using to deal with those. Now, if we have a laminate, we can have stress-strain behavior like we've been seeing with our metals. That's that third figure there. Typical stress-strain curve if we have an aluminum layer, something like that. We can have brittle material where there's very little yielding, like the first chart here, linear elastic. That's how a brittle material will often behave. We could have elastoplastic behavior where it kind of goes up a linear curve of some kind and then flattens out. And we can actually have nearly any other subcombination among those. Now, once we understand the lamina, and we haven't learned anything about that other than to just get some concepts under our belt so we can communicate with the same language, we're going to start dealing with the laminate, which is a stack of more than one lamina, more than one layer. So a lamina is composed of 2 or more layers, or lamina, and it's going to allow us even more options for engineering our properties. Okay, and here's a little example of a 5-ply laminate. We've got one, let's say that the 0 direction is loaded. Let's say that we've defined this as the 0 reference direction. That means the first layer is in the 0 direction. The second layer looks like it's about 45 degrees. Hey, no. The third layer is at 90 degrees. The next layer is also 45, but it's the other 45, so it's a minus 45. And then the last layer is back to 0. So that's how we're going to be dealing with those kinds of things. Okay. Let's go back to the idea of macromechanic versus micromechanic. Micromechanics, once again, is when we're going to go and look at, we're really not looking at the microscopic level, but what we're saying is we're going to look at the constituents of a layer, and we're going to deal with those properties to estimate the properties of the layer. So when we're looking at the property of the fiber and the property of the matrix, each on their own, that's called the micromechanical level. When we talk about the macromechanical level, what we're really talking about is the behavior of the entire layer. So for each layer, we need to understand its behavior in its 3 perpendicular directions, and we can sometimes get that directly from properties, from tested properties, and sometimes we will estimate those properties from the constituent values. When we try to estimate that from the constituent values, we're talking about a micromechanical level of analysis. And once we have the properties of each layer, we're going to call it a macromechanical level. And once we have the macromechanical properties, we're ready to go start and evaluate the laminate using classical lamination theory. That's where we're headed. Okay? So we can have, what we're going to be dealing with a lot with fiber reinforced composites. These are very popular. The fibers enable us to bring very stiff, very strong materials into the mix. And this is one of the current modern ways of getting really engineered properties for what we need. We also use a wide range of other things like short fibers, particles. A lot of times the particles that you may see ceramics, especially for high temperature. And then sometimes, so a lot of laminated materials may be isotropic materials or pseudo-isotropic materials. You might have aluminums with a balsa wood core or something like the old floor panels in a number of aircraft, and any combination of these. We're going to be dealing with sandwich kind of structures also in this class a little later once we get classical lamination theory under our belt. So let's look at some of the constituents that we're going to be dealing with a lot. The first one is fibers. We could call the filament the basic structural element of the fiber. It's basically a continuous element, like a little string, about 5 to 10 microns in diameter, and it's very long relative to its diameter. Now, we like to think of that, each fiber is running from complete end to end of the fabric, but that's nonsense. They're like string. They have lengths, and these lengths end at different times, but acting all together, even though all these are discontinuous because they all end somewhere, the way they bond together, just acting alone, they still get some very strong properties. Now, when we talk about a yarn, we're talking about a bunch of filaments that are twisted together to create a little more stable string-like element. We're going to call that a yarn. Typically, these are going to be 10,000 or fewer filaments and are often continuous but not completely. Okay? These are more common for like fiberglass composites. Now, we use this word tow is another, so we could just call this loosely strings, right? A filament is one little element within the string. A yarn and a tow are just two different words for that. Once you have a bunch of these little strands of your string, that's what we're dealing with. One of them, the word yarn, is used when we have these twisted together, and a tow is the word we use when they are untwisted together. So you just kind of lay them together. The yarn is twisted and the tow is not twisted. These are typically 3,000, 6,000, 12,000 filaments per tow. Smaller sizes are often used for weaving and winding because you're getting disruptions as you go around. The thinner they are, the easier it will be to weave. We can also, these tows are also sometimes called a roving or a strand. These are all nearly synonymous words. Carbon composites, graphite epoxies, those kind of things. Carbons are typically offered in these tow kind of bundles, where the fiberglasses are more commonly with the yarn. Okay, so materials in our fiber form tend to be stiffer and stronger. We've already said that, and we characterize that with a high length to diameter ratio. So basically, we all kind of have some familiarity with the property of strings and ropes and things. You pull on them, they're very strong. You push on them, they have almost no strength. You bend them, and they have almost no bending. That's basically what our yarns and tows are going to be having. And the fibers within that are like that. Here are some typical properties of some fiber and some wire. This is out of Jones's book here. And some typical densities and tensile strengths. You'll see we're talking here KSI, right? E-glass is 500 KSI for strength. Boron is a 500 KSI strength. Graphite is like a 250 KSI strength, as opposed to aluminum, which at best is 90-ish KSI strength, more like 60 to 70 to maybe 80 KSI, with similar differences in the modulus. So these are typical wire and fiber properties. Okay. Now, what properties are we going to be using? Well, the properties we're going to be using for our analysis, because we're going to be doing micromechanical and macromechanical analysis in this class, and we're going to be pulling properties from Appendix C. So Appendix C has the properties for this is for a fiber. So if we're trying, and the time we're going to use the fiber properties, and so when we get to the chapters and the sections, on micromechanical analysis, when we're taking the constituents, the fiber and the matrix, and trying to predict the behavior of the lamina. That's where we're going to need fiber properties. These are two tables. One is US units, one is SI units. We only have a handful of properties. I'm using cause properties here, as you can see the table. The reason for this is we at one time in the past used cause as our prime text. It's a good little book, nice, not too complicated, does a pretty good job. And so because I developed a lot of content around these properties, I'm reporting these and using these for my class. So we've got graphite, we've got glass, we've got aramid fibers, we've got Kevlar fibers. In the future, I will probably add more properties to my text and to this class. Right now, these are the ones we're going to be playing with as we learn our methods. And some of the other books that I provided book reviews on, like Barbro's book and Jones' books, have a wider number of sets of properties available. So here are some fiber properties. You don't need to copy this because it's in your text in the Appendix C. Okay, this is where we're going to get the same appendix. Next little subsection is where we're going to get our matrix properties. Remember, we're going to have a fiber and we're going to be burying it in a matrix. So here we've got epoxy, aluminum, polyamide, and PEEK. Well, if we have aluminum, we're probably not burying any fibers in there, but if we have epoxy or polyamide or PEEK, we might. So these are some matrices that we will be using with the properties we will need when we're using those in US and SI units. So we also are going to need, once we get past the micromechanical level, so remember we're going to use those micromechanical properties, fiber and matrix, to predict what the lamina, how the lamina behaves. But often we're going to be doing analysis of lamina and we're going to say, hey, we got a graphite epoxy. In that case, we're just going to come here to this table and use the properties from here. These are also from cause, book, and same value. These are typical values, but these are the ones that he uses in his text, and that's the one that I've been using in my class as well. If you want a little more information on that, and you want to look at some of the examples he has, go ahead and grab a copy of his book, and that can help you to give you some more further reading. A lot of times we're going to use a little element symbol like this little upper right corner where we have this. It looks like we've got the fiber represented and the matrix represented. And what we're trying to show is that we've got a fiber and a matrix, two distinct properties. But actually, once we construct this layer, this lamina, it's going to be like the whole thing. Everywhere we are is going to be the ratio of fiber and matrix, and we can kind of pretend like it has the orthotropic properties that are given here. So you can see we have orthotropic properties because we have a modulus. If we're looking at the glass epoxy, we've got for a fiber volume fraction. We'll learn more about that later. This is about 45% fiber, this first one. The boron epoxy is at 50. These properties are about a 50% fiber property. The graphite epoxy is about a 70% fiber, and the Kevlar is about a 60%. For that, if we go back to glass, we see our longitudinal modulus in the strong direction is 5.6 million psi, and in the transverse it's 1.2. Transverse being the widthwise direction, but we can use that actually for both width and thickness if we need a value. The shear in plane modulus is 0.6 MSI, and so on. You can see Poisson's ratio, you can see coefficients of thermal expansion, you can see here compression and tension strengths, shear strengths, and so on. Some of these values are not from cause book. Most of them are. Some of them I have estimated, and some of them are from other references. Okay, so that is the kind of data we're going to be needing to hone our abilities in composite analysis. We've seen this chart a couple times where we've looked at the different kinds of layers. We may have a unidirectional, which we're calling continuous here, a woven, or a oriented or random, or other combinations of materials. So let's look at how so a unidirectional fiber means all the fibers are in one direction. That's going to give you a really strong, stiff material in one direction, but the other direction is going to be weak and less stiff because it's going to be relying on the matrix for those properties. If we lay the properties on top of each other, then we have potential to get better properties in both perpendicular directions. The problem is these fibers will tend to split apart under loading. So we have various scenarios for weaving those fibers together so they act as one. And that's where woven fabrics, just like the weave on your shirt. The simplest one is a plain weave, where every fiber goes over one, under one, over one, under one, and the same thing in the other direction. As you can see here, we can show the pattern like this, or we can show the pattern like this, which shows that each fiber is going over and then under each adjacent fiber. And here's some information on that. The lino weave is kind of interesting. It's kind of, actually I probably should have put that first. That's like a unidirectional fiber, which then has some much smaller in the weft direction thing tying those yarns together, but not necessarily giving the same properties. The basket weave is where we have, instead of, remember with the plain weave was one fiber going over, under. The basket weave is almost identical, except now we're going to have two fibers going over two, under two, and in the other direction too, over two, under two. And that's how this one looks. Okay? This is going to tend to give us, because now each time we go over and under, it tends to make the more crossovers, the more stable or less liable for everything to come apart. But it's going to make it stiffer in the sense of being hard to drape. We call it drapeability, how we can, like if we have a curved shape like a rocket nose or a missile nose and we want to drape that composite over it, the more intersections of the fiber, the harder it is going to be to drape it. And the less intersections, the easier it is. So a basket weave is going to be really similar in properties to a plain weave, but it's going to tend to drape a little better, and with a slight loss of stability. The 2x2 weave is the similar. We've got now, instead of 1 and 1, and instead of 2 and 2, it's like 2 and 2, except what they do is they have 2 and 2, but the one of them is offset slightly in its weave pattern like this. So each yarn will go over 2, under 2, but you'll notice the 2 are offset. This first one goes under 1, over 2, under 1, while the other one has a different, it's offset by a factor of 1. Now what this does is this gives a nice diagonal pattern that looks really cool. So a lot of composites are made with this because of the cool looking pattern. And it tends to be a little better interlocked than the basket weave, but not as tightly locked as the plain weave. So it's a good middle of the road kind of material. And then we get to the satins. Now the satins are similar, but what they do is they go over one and then they go under some number of them. Common satins would be 4, 5, 8, and so on. So the satin number, like a 4 harness satin, which is what I drew here in this upper picture, means the pattern is 4. If you look at this mnemonic down below, you see what we have is, if we trace this fiber here, it goes under 1, over 3. So the total pattern is 4, and then it repeats. That would be a 4 harness satin. Now if we look at this guy here, we see we're going 1, and then I was under, and then over 2, 3, 4, 5, 6, 7, 8, and then it goes back under. So that pattern is 8. So this down here is an 8 harness satin, while this up here is a 4 harness satin. And it does the same thing in both directions. Got it? So those are commonly used when you need more drapeability. We use these on the Delta 3, Delta 2, and Delta 4. We use the 5 and 8 harness satins. This is another way of looking at these two pictures. These are from Ramadan's notes from a class he used to give McDonnell Douglas and Boeing. And this is just showing, once again, kind of loosely. Here's a plain weave, a 4 harness satin, a 5 harness satin, 8 harness satin, and so on. And warp, once again, is that longitudinal strong direction, the direction the main fibers run in. And the weft or the fill direction is the widthwise direction of that. It's the transverse direction, but in the plane of the cloth, not through the thickness, which we often call the transverse. So I'm going to use that warp and or longitudinal and widthwise term a lot, while warp and weft or warp and fill are another more precise way of referring to these ideas. So now that we kind of understand some things about the terminology and we understand some things about microscopic, macroscopic, we know where to get our properties, we know that we're going to be able to predict properties from the microscopic elements, from the constituents at the lamina level. Now we want to start preparing to deal with composite laminate theory for dealing with a laminate. In order to do that, we're going to need to not only understand each layer, but we're going to need to understand what's the orientation layer. Like if we look down here, we see we've got a certain layer of material. You'll notice now on the drawing, they will often call out, or should call out, what is the reference direction for the material, and then each ply will be laid out and will be referred to what is the angle that it makes with that reference direction. So this looks like a 30-ish degree property. So here, if we have this is the reference direction, this is a 0. This looks like a pseudo-isotropic material made of little powders or flecks or flakes or grains in another matrix. And the next layer looks like we have little short fibers, which are all mixed together. And then we see that weird looking one. Actually, that's what these fibers look like if they're off at an angle. Now, if they've been in this direction, they might look the whole length. If they're going in the 0, get down. Do you mind? Jump, down, get down. Get down, we'll play later. If they were going in the longitudinal direction, you'd see a bunch of little ends that are cut off. If they're going in the transverse, right in the 90-degree direction, you'd see the fiber running all along. But if they're at an angle, it cuts a cut through the thing, cuts a nice oblong kind of thing, and that's how these look when they're like a 45 degree or something. Anyway, so that's how we're going to, so we need to define what each layer's orientation is. So we're going to do that with what we call the laminate code, okay? What this code is going to consist of, it's going to consist of a pair of brackets. That's what we're going to use to differentiate that. And then we're going to lay out the orientation. So each number is the orientation of each layer, going from top to bottom. So this is the orientation of the top layer, next layer, next layer, next layer, bottom layer. That's how we're going to do that. Okay? And then we're going to have, so we see here, we've got... this is a 0 degree. The next one is minus 45. And this is a different call out than what we're showing here, by the way. Minus 45 degrees, 90 degrees. That's transverse to the original layer. 60 degrees, 30 degrees. Okay? That is one way of calling this out. All right. So, once again, brackets are going to enclose this laminate code. We're going to use slashes to differentiate between the different layers. We're going to use numbers. Up here we've got 0, minus 45, 90, etc. Down here I'm calling it X, Y, Z. Each number gives an angle of the next ply. We can use subscripts and superscripts. Subscripts will often give information like, hey, this is the total laminate, or this is symmetric laminate, or whatever. Superscripts can be used to indicate what the material is. We can also use superscripts or subscripts for how many layers are repeated. So, for example, this one here says that first orientation, X, is of an aluminum material. The next one is of a graphite material. The next one is of a glass material. Now, if they're all the same material, we just call out that material and we would just show the code with no material information whatsoever. But if they have different materials in different layers, we need to make that clear, and we use superscripts to do that. Okay? So here is a typical kind of call out we were talking about. This next call out with the T just means total. When you see a little subscript T, that means that's the entire laminate. There's no other layers. It's kind of superfluous. You don't need it because just seeing this first call out and the second call, these are identical. The only thing is the second one is explicitly reminding the reader or the engineer that this thing is everything. There's not anything else. Okay? This little subscript 2 on the 90 ply says there are two 90 plies in a row. So we'd have a 0, minus 45, 90, another 90, a 60, and a 30. That gives us what we call condensed notation because we're actually referring to layers which we're not showing. And expanded notation means we're going to define what every single layer is. Condensed notation is we're going to use the maximum compression of that indicator to make it as short as possible. And one way to, so expanded notation for this one would be 0, minus 45, 90, slash 90, 60, 30. Condensed notation would be 0, minus 45, 90, subscript 2, 60, 30. Got it? So this is expanded notation. We could have used a 60 there in the middle with a 2. Or, since this is, you'll notice if you put a little, let's just imagine a mirror right here reflecting this way. If this half of the laminate stood looking into the mirror, and it would see exactly itself reversed. You'll notice this is symmetric. These are the same, these are the same, these are the same, which means this is symmetric about the middle. So we actually could have called this out. This would be expanded notation. We could have called this out by using 0, minus 45, 60 with that little subscript S, which means it's symmetric, which means after the 60, we're going to repeat everything that was before it, but backwards. Okay? Another way to call this out, we could say 0, minus 45 and use the overbar. The overbar means this is not repeated with these other pieces. So this says 0, minus 45, 60 is symmetric. Now, if it were truly symmetric, there'd be two 60s. But with the 60 overbar, this says 60 is not repeated, which means this is actually only symmetric through the middle of the 60. It's not symmetric through the side of the 60. So this would be a 5 ply, while the prior one is a 6 ply. These are not identical callouts. Okay? This says we've got a, this looks like a 1, 2, 3, and it's symmetric, so 6 plies. We've got a 0 direction graphite epoxy. We've got a plus and then a minus 45 boron. Then we've got everything backwards. So a minus 45 boron, a plus 45 boron, and a 0 degree graphite. Expanded notation once again calls out every single layer, and condensed has the max compression using this kind of terminology. So that's how we identify laminate codes. Obviously, if we can't understand laminate codes or refuse to master that, then a lot of composite laminate theory we're going to do is going to be a complete waste of effort because it's going to be analyzing something that we don't have. So it's critical to understand this simple little concept. Okay? So there's a bunch of abbreviations used in composites, and the problem with those is unless you're working with a bunch of people that have the same terminology, you can get a little confused and make mistakes. One is CFRP, carbon fiber reinforced plastic. This word plastic, you know, we used to think of cheap super balls coming from certain third world countries when we talked about plastics, little rubber toys and things that I used to enjoy as a child. But plastics is a general term that refers to a wide range of plastics and thermoset resin products that have some very powerful capabilities. So that plastic word is a bit of a loose term. Prepreg. Now this word prepreg, remember we've talked about fibers and matrices. One way to make a composite is to lay out your fibers. Let's say we are making a rocket tube, and so we wrap our fibers around a mandrel and lay them and then wrap them. But then we've got fibers, we don't have any matrix. So one way to do this is to brush that epoxy or whatever our matrix material is on the fibers until they get fully wetted and they absorb that. So it's between the little strands, the little strands of each toe or yarn, and around them, so everything's wetted, so everything is wet with this. It's kind of like if you wad up your shirt and you dip it in the pool really fast, sometimes only the outside gets wet, not all of it. But if you set it in there and then pull it out, now it looks like you don't have any water in it, but it's all permeated throughout with the water. There's no extra freestanding water anywhere, but the water is soaked it through and through so that every piece that touches another piece is wet, as well as being wet all throughout the fabric. That's what we're talking about, that we're going to need to do when we're creating lamina of multiple materials. When we have a fiber and a matrix, we need to wet that fiber like that. Prepreg is a way of impregnating the fiber with the matrix. One way of doing this, when I was at SciTech, we were qualifying them, or trying to qualify them for a second source for graphite epoxy material on the Delta rocket. We went out to their plant, and what they do is they'll often use a thin sheet of paper, and they will mix up the resin so it's nice and uniform with exactly the properties they need. Then they will take it out and they'll drop it onto the sheet of paper that will roll out until they get a nice, precise, measured, uniform thickness all the way across. And so everywhere they're checking the thickness everywhere to make sure it's all uniform. Then they make a roll of this epoxy sheet on paper, and then they will go and they'll weave their fabric, and then they will take the roll of the paper with the resin and a roll of the fabric, and they will roll them out so the sheet of resin lays out. They drop the fabric right on top of that. They take another sheet on top of that, so now the fabric is sandwiched between two paper sheets, each of which has resin on the other side, and then it's pressed together with an engineered pressure and temperature to impregnate that cloth. And when they're done, and then they roll that product up, and now they have a woven, it could be unidirectional or woven fabric that is already impregnated well with the resin, completely and thoroughly. That's called prepreg, and that is how a lot of these composite materials, when we have a fiber reinforced composite, how a lot of these are handled, because it makes it easier to handle and easier to build and things like this. So here are some terminology for the resins and materials that actually, if you take our class at in the material science on composites, they're going to focus a lot more on the constituents. They're going to go way down even deeper into the microscopic phase, along with the materials of the fibers and the resins and the different stages and the cure processes to give the maximum capability, or the engineered capability you need. And I'm just going to kind of brush over this and leave that to the materials guys. I'm going to focus more on the analysis side. Some of the books like Jones and Barbaro and Kaw deal with that in more detail, and News book as well deal with that in more detail. But we're going to basically say, hey, we've got fiber and we know what the properties are. We've tested them. We've got matrix. We are using compatible materials to make sure that they will work together. That making sure that they're compatible is a whole nother science that falls into that materials realm. We're going to kind of brush over that and stick with the analysis in this class. Okay? this is looking at, okay, so remember we're going to be taking the fiber and we're going to be dropping it into the matrix. Now, as we talked about, these fibers, while they are long and continuous, they aren't infinitely long, which means there are ends of fibers all over the place. This is one of the reasons why we need the matrix. If we, so actually what that means is we have this impregnated fiber and there are ends different places. Now, theoretically, if this is well created, these ends don't all align. Or basically different ends could happen anywhere. At any given cut, you could have an end or multiple ends, but there aren't very many in any given spot because they're so uniformly prepared. So actually we have defects everywhere. Because there are defects everywhere where these little ends are, that means when we get damage like a cut fiber, it doesn't really change the properties much a lot of times because already the properties that we've been measuring have a lot of discontinuous spots in the fiber. Now what happens when we have continuous fibers with one fiber that's now discontinuous like we see here? This is a picture from Jones's text. What happens is when you pull on this, all of these try to strain the same. Now since that one can't strain the same, that one has all the load, whatever force, whatever stress is in this fiber that's discontinuous, can't go straight down into the rest of the fiber because it's not attached. What it has to do is shear into the resin or the matrix material and then shear over. So you could just kind of imagine it's like the resin is this, here is our fiber and it's sitting here, and when this pulls or pushes, it's got to shear through the matrix and then enter the other one. This is going to give us a very complicated nonlinear distribution of load transferring in and out of that fiber. Almost none of it will actually be able to be carried in tension in the matrix, but it will shear out. As it gets closer and closer to the end, it's kind of like you're running at a bridge, and the middle of the bridge has a big hole. All the cars are going to be trying to go around, and what's going to happen is you're going to get a tighter concentration right along the edge of the hole. But once you get close, everybody's moving to the side, nobody's moving forward. It's got like no stiffness, and this fiber can kind of sense that dropping stiffness because the only stiffness of that discontinuous fiber as it gets near the end is based on the shear stiffness. So that's what this kind of talks about. And this, we'll may deal with this some more when we get to the damage tolerant kind of things that we're going to cover. Now I decided to remove the damage tolerance content out of my text to keep it concise, and because I really didn't have it developed to the level where I really want to preach the methods that I'm teaching my students yet publicly, I recommend, actually Barbaro does a really good job of that, and Jones does a fair job of that as well. So if you want to study that out further, great. What we want to learn from this slide is that we need to have this fiber impregnated. We need to have the matrix fiber combination uniform, and we're going to have discontinuous fibers all over, both broken ones and just ends of ones, and that's going to give us it's going to actually affect our properties, but because we're measuring the properties with all these discontinuities that are kind of randomly distributed throughout the material, we're going to end up any little given defect is not going to have nearly as much effect because we already have accounted for a lot of defects within our material. Actually, Jones does a really good job of talking about that in his text. Okay, so our focus is going to be on fiber reinforced composite materials. We're going to be learning to deal with the constituents and then getting the properties of the lamina so that we can do the properties of the laminate. Let's look at a couple conceptual questions. What weave pattern is this? So think about that a moment, and once you may want to stop the video. Once you have your answer, then you can see this is a plane. We're going over and under. This is a plane weave. How about this guy? This is not going over under. This is not going 2 by 2. This looks like a pattern of 4. We're going under 1 over 3. This looks like a 4 harness satin. How about, are the properties of a lamina considered macroscopic, microscopic, macroscopic or microscopic, right? It's macroscopic. So remember, the lamina has fiber and matrix, and when we deal with the properties of those to estimate the lamina properties, we call that micromechanics analysis. But the properties of the lamina itself, once we have those, we're going to call that macroscopic analysis. We're going to be using that in our classic lamination theory. Can a lamina be isotropic? Sure, of course. Can a lamina be anisotropic? Also, yes. It can be basically anything as long as it's roughly homogeneous. Can a lamina be inhomogeneous? Oh, I just spilled the beans. Not really. When I say not really, what that means is no, it can't, but there are a lot of things that are inhomogeneous that we're kind of close enough for government work we can kind of pretend they're behaving homogeneous in a homogeneous way. Welcome to engineering. So that is our second lecture for our composites class. This is these first two lectures have kind of been high level looking at the stuff, and many other texts go a lot more into detail in some of these materials, spend more time just talking about these conceptuals and how it works and things. We're going to be jumping in with analysis starting next lecture. See you then.